Okay, so is there any question related to heuristics, labs, problem sets? Good. So going back to what we were discussing earlier, we said we discussed the ISAs, and then we want now to understand how does the hardware really implement the ISAs. And we built a subset, 6 instructions that we said represent most of the bases of the data flow and the control flow. They represent most of the instructions. And we started building the data path one by one. We started by the add instruction, then the add I instruction, and then the load instruction, and the store one. And then last time we stopped at the control flow one, the branch equal. Right? We know that from the ISA lecture that the branch equal would have a 16-bit immediate value that simply represent the offset that I want to jump to once my condition is true. How do I evaluate my condition? This is branch equal, so I'm going to compare these two sources. If they are equal, I'm going to use this offset to jump. If they are not equal, what's going to happen? Just ignore the jump address and continue for the subsequent instruction, right? For this to happen, we now need to, and this is where the change comes from, well, compared to the previous case. Here, all the fetch logic would in fact assuming I execute one instruction by 1. So all with an increased program counter by 4, right? But when it comes to the branch equal, I now need to update the program counter with a different address, right? And we discussed in detail for the branch equal I type instruction how to compute that address, right? We said you have 16 bits, so simply you need to sign extend the 16 bit to 32 bits, and then you shift left to match. Well, again, you shift left by 2 bits. Again, one shift lifting by 2 bits. So one step back, just make sure you follow. I have the immediate value, which is this one. I need to extend to 32 bit. Why do I need to extend to 32 bit? Because I'm adding to the program counter. So you need to add 32 bits to 32 bits. So I sign extend them, but then I'm also shifting left by 2 bits. Why that's the case? Instructions are 32 bits, so 4 bytes, and I jump by instruction granularity. This is why again I'm shifting by 2 bits. And then simply I'm adding this to the next program counter. So it's program counter plus 4 plus my immediate address. So if you look into that logic, we need it. This is again our style is that anything we add newly to the data path is going to be in red. So I added this whole logic to really execute that equation, right? Now, there is one thing that I need to pay attention to. I'm only doing this if my condition is true, right? How do I know my condition is true or not? You need to go through the ALU, right? So you need to go through the ALU to conduct the subtract operation, because you need to subtract these two. How do you check if they are equal? You subtract, and if the result is 0, that means they are equal. That's why we are taking the output of the 0 flag from the ALU and feed it to basically an AND gate to determine whether I should jump or not. So I'm subtracting the two sources. If they are equal, then I'm going to use the path where it comes from the adding. Otherwise, if they're not equal, I need to use the normal path. The program counter again takes two different inputs. The usual one, which is this black one that is coming from just adding 4, or it takes a one that simply adds all these equations, which is this red logic. But this happens only if the 0 flag is set, which means your branch equal condition is true. For the jumps, the main difference between the jump and the branches, like the conditional branches, is we have an absolute jump, right? So why our immediate is a bit larger, it's 26 bits. And then in that case, I don't have a condition to calculate, right? So I'm not using the ALU for any calculation. Instead, I have the immediate value that I simply, shift by 2 bits as we discussed earlier, and then you pad it simply by, you shift left by 2, and then you take the last 4 bits of the program counter, and then you simply pad them together, right? And once you do this, you have your absolute address. So let's see how this is really happening here. First of all, shifting by 2 bits is happening through this shifter, right? So I take the immediate value, shift it by 2 bits. Then I need to pad it with the last 4 bits of the program counter, which is this basically dotted line. Why I have it as dotted line, not as a function unit or circuit? Because again, it's just like padding. You are adding wires together, right? You're just concatenating a wire to another wire. And then now you have your full 32-bit jump address. Well, do I jump or not? I have another multiplexer here. So remember that this whole logic, this one, is the branch equal stuff, right? This is the conditional branch. I added another multiplexer here. Why that's the case? Because in the case of a jump, I don't really take that path. I take a completely different path that is coming from the immediate value directly, right? So I need, in fact, another multiplex. Good. So now we have the jump logic as well. So I can keep adding instructions as I wish, but you will realize that simply the add very related to the data path right now. For example, if I want to add a shift logic, well, the shift and the logic operations happens through the ALU, but to simplify things, they add shifters inside the ALU, right? So shifting instructions are usually done by shifters, which means they are really wire. It's one of the easiest circuits, basically wire shifting. This is the jump and link instruction that we're discussing right now, right? If you want to, again, do a functional code, you use the jump and link, and you have an absolute target. So simply it's like jump, but you need to write program counter _ into the RA, as I explained earlier. If you want to jump register, if there is an IC that supports jump register, where you get your absolute address from a register, not from the offset within the instruction, then simply go ahead, read that one from the register file, load it to the program counter, and you are done, right? Make sense? So you can keep adding things, but well, the more your data path becomes mature, the less you need to add to support other instructions. Okay. So now, given that we are done with the data path, we added all our needed components for the 6 instructions. We need to add the control. What do I mean by the control? So if you look into what we built so far, we had so many signals, like for example, the multiplexers that have selection lines, the ALU that tells you that you need to do an add or subtract, the enables for the data memory and the register file. So I had multiple signals that control what operation do I do. These signals are created by logic, right? That, well, you need to figure out based on whether I have an add, what I feed to the ALU operation. Whether I have a load or store, well, whether I have a store, then I need to enable the data memory write enable, right? This kind of logic needs to be built, and this comes from the control unit, right? What we call the control path is simply the circuitry that creates all these enables and controls of the data path. Good. Right now, so far, we have a total of 9 signals that controls the data path, including mux selectors, register memory write enables, what type of the ALU operation. In reality, if you have a very complex data path, you might have hundreds of control signals, right? Now, how do I build the logic that comes out with these control signals? I have multiple options. One option could be, okay, I go through all my instructions, have a table that tells me for all the select signals. In our case, they were these 3, 3, 8 ones. I say, okay, for the add, what are the values that I needed to build, right? So let's take the add as an example. For the add operation, first of all, in an add, I don't have a branch, right? Let's go through first the selection lines themselves. BR here, that's basically saying that branch, this is a selection, this selection line, whether you have a branch, a conditional branch or not. And jump is the selection line for the second multiplexer, whether you have an absolute jump or not. Data memory enabled, that's basically this one for the store. Register file enabled if you want to write to the register file from that instruction. And then ALU operation is the one that is determining whether you need to do an add, subtract, multiply. And then ALU input B. Remember, we added a mux here because we had 2 options. One for the absolute add, where I'm taking my 2 sources from the register file. The second one is the add I, where I'm adding 1 source to the immediate value that was in the instruction. And I need to add a mux to simply select either that path or that path, right? This is the meaning of all these signals. If you're not able to follow, let's wait for a second and ask questions. Because if you are not understanding every single meaning of the signal, you'll not be able to follow how we create the logic. Is anyone confused about the meaning of any of them? Great. So for the add, what are the values? First of all, I don't have a branch or jump, so it's easy zeros. I'm selecting the first path here for the register file, so I'm setting this ALU input to 0 to select the first input of the mux. ALU operation is 0. You have to trust me that 0 is the very first operation in the ALU, which is an add operation. So it's 0 here. And then I don't write to the memory. So write enable would be 0. But the add operation is going to write the result to the register file. This is why I need to enable the register file write enable as 1. And you have a destination here. So where do I need to get that thing is from here? So remember, there was another mux that we needed, especially for the load operation and the arithmetic operation. Before we add the load operation, for a normal arithmetic operation, you finish your ALU output, you write it directly to the register file. For example, add R1, R2, R3. Simply the result will go to R3 directly out of the ALU. But that's not the only way you can write to the register file. If you have a load operation, you're going to go to the memory, bring a data, and write it to the register file. Now the register file needs to take input from 2 different places, the memory and the ALU. That's why we have a mux here. This mux, if it's simply 0, like this register write destination, if it's 0, it comes from the ALU. If it's 1, it comes from the memory, right? That's a simple single bit selection line. In the case of an add, I'm setting it to 0 because again, I'm getting the result directly from the ALU. Make sense? So understand why the values are like this for the add. So if you go back to the bigger picture, how does the processor execute that? First of all, the instruction is in the memory. I get the program counter, go to the cache, bring the instruction, then understand it's an add operation from the opcode and the function bits. Then the control logic through the decode stage will create all these signals, feed them to the data path. Once the data path is enabled like this, it will run, do the addition, write the result to the register file, and then you are done with the operation, right? So you simply fetch, decode through the control unit. Decode means create these signals and then execute. Okay. So the same thing would happen for the other instructions. For example, if you have a store, things will become a little bit different right now. Again, I don't have jumps or branches. This will remain 0. But in case of a store, I need to enable, for example, the data memory enable. So this has to be 1, correct? This thing is don't care because in fact I don't write to the register file at all, right? You always write to the memory. And then, well, in case of a store, I need to use the ALU to calculate the offset address. So you are using that simply, you are taking one input from the register file, the second one from the offset itself of the immediate value. So you have to set this to 1. What else? Yeah, I guess that's all. Well, something different from the add is the write enable for the register file is 0 because store does not write to the register file, right? So it's a very good exercise to look into the second instructions we have went through and try to create the 8 signals to see how, in fact, the data path will execute them. What control signals do I need? We have done the add and we have done the store. Okay, so we have done the store. Branch equal, well, again, you can go through the logic itself. The thing that might be different in the branch, again, I need to enable the branch path, right? So I would have a 1 here to select that one, instead of selecting this one. In case of branch equal, I'm still using the ALU. And in fact, you are using the ALU with the 2 input operands. So you have to set this to 0. In the branch, you don't write to the register file. This is why you have to set this to simply X, right? And this also X, which means there is no destination. You don't write to the memory, so write enable is 0. It's not an absolute jump, so this has to be 0 to select that path, right? Makes sense? Good. So again, just to explain to you what happens, I have the program counter. In the case of a branch, I discover it's a branch operation. I'm using the 2 operands in the branch from the register file, subtract them, take the 0 flag. If the 0 flag is 1 and they are equal, I'm setting that path, which means take the actual address that is coming from the branch equal, and then I need to feed it to the program counter. So I go through that path, and then I have to select that one. To select that one, jump has to be 0, right? And then you write it to the program counter, and then you are done. Good. One thing that might be related to lab 2, just to give you a hint into the lab, and then hopefully you would have a separate detailed lecture for it. For case of branches, especially, there is a little bit of a problem right now, especially if you have a pipeline processor. This problem is, if you don't have a branch, like let's say in case of the store or the add, you know beforehand, before you finish the current instruction, that your next instruction to execute is the one that is program counter plus 4, right? So the flow of the program is known, which means if you have a pipeline processor, as we said earlier, once you start executing the current instruction, you can allow the program counter to fetch the next instruction from the instruction memory, right? And hence you can really, well, have a flow of instructions coming through you. The problem with the branch is that this doesn't really happen. It's not possible. Why? Because I don't know what is the next instruction to execute until I finish my branch, right? Why? Because, well, it can be the next instruction if the branch is not equal, in case was equal, or it can be the one I need to jump to. So branches, this is why they are called control flow instructions. They simply control which instruction you execute next. If you think about pipelining, it just kills your pipeline, right? For that reason, handling branches effectively would impact performance problem. How is control implemented? So we said, okay, we have all these signals that we want to create. I can implement the block that I call control unit using multiple things, multiple ways of doing it. So one way could be, well, since each instruction has a unique set of control signals, we said the add has its own 8 different signals, the subtract would be the same, the load would also be having their own set of control signals. Then in this case, I might be able to, well, have a lookup table, something like a ROM, for example, where I access that table by the instruction opcode and pick up the bits from the lookup table based on the type of the instruction. So this an add, pick these 8 set of signals. If it's a load, pick these different 8 set of signals, right? So use a simple lookup table. The problem with this is, well, if you only have 6 instructions, then you have 6 entries. If you have hundreds of instructions, you have hundreds of entries. And we only had 8 control signals. If you have hundreds of them, then you really, your width of the lookup table would be hundreds of columns, right? So you need a lot of storage to store that, right? So having a lookup table would have an area disadvantage. But what might be the benefit of the lookup table? Fast, very fast, right? Thank you. Because I don't need, in fact, to calculate stuff, right? I just have the opcode, go ahead, bring the actual control signals, right? So it's very, very fast, but consumes a lot of area. And this is why, again, generally, not even in computer architecture only, but in any digital design, people usually tend to use lookup tables if they care a lot about performance and less about area, right? So it just comes to mind that, well, this is the solution, right? If you don't have an area issue and, well, the lookup table size is manageable, use it, right? For example, in networking routers, right? Like the way you really route packages through very fast lookup tables, right? Through the routers. Why? Because you care a lot about the performance of the network and less about, well, how much storage you need, right? Good. Then the second one is the other way around. If I want to minimize the area, but I want to calculate the signals on the fly, then you create a finite state machine, right? You simply go to the digital design course, go to, well, Maurice Manu's book, and then say, for each signal, I have a Karnaugh map, or simply I have a set of inputs, which are the instruction opcode. I know that this bit is 0 here, or 1 here, or 3, like, don't care there. And then create the custom circuitry that feeds this signal, right? So you create a finite state machine that outputs the control signal. If you go with the ROM, again, like, that's simply something that is good. Well, we say it's ROM because you don't need to overwrite it once you already store it. But you might end up having something like this. I have, well, all my control signals as columns. I have my instructions are the addresses that I go there and feed. And then simply with the opcode, I address a certain entry, bring the data. Good. Yeah, we said, well, again, the problem with the ROM is might not be, well, it depends on whether you have 4 kilobytes within your own data path or not. Here it says, okay, but hard to make fast. It depends how you implement it, right? But it's definitely can be faster than what? Here they argue that if it becomes too large, it also becomes slow, right? Because you need to address it, right? So the idea is, if this is manageable, and we'll have this logic of discussion a lot when we talk about caches. If you think about why your L1 cache in your processor is very small, like in kilobytes, It's because it's expensive, that's one thing, but definitely because you want to make it very, very fast. If you start making your memory large, this indexing logic to go to a certain address would take some time. And that gets the searching the certain index is going to consume some time, right? So the head latency in that table will increase. So there is a certain limit basically that you can go through. And then the combinational logic you can optimize based on every single individually. And then, well, it will take, might be less area, but it can be faster, or if you have a very large thing, or it might take less area, but it becomes very, very slower if the size of the table is manageable, right? But if you want to control your logic, you can have something like this. I get the opcode as an input. Here you have something like a DMux or a decoder assembly that gives you all the instructions. Then say, okay, for each signal, how do I create the logic of this? If you go through the table we have here, and that's also another good digital design exercise, these are your outputs, and these are the inputs of your instructions. If you want to optimize the circuit for each one, you can simply create the circuit your own, right? One very simple thing is to say jump B is one only if this is a jump, and the branch is only one if this is a branch. If you go here, you find that we only took the jump and we took the branch, right? Here, for the register file write enabled, when do I write to the register file? It's an add or add operation, or it's a load operation. That's why there is an OR gate here that says if it's either one of these three instructions, just really enable the write enable, right? When do I write to the memory? So is the memory one here? I write to the memory through the store operation only, right? This kind of stuff, right? Okay, makes sense? Okay, so there is one additional thing to discuss that will take us to the topic that we're going to discuss tomorrow, which is related to pipelining. We didn't discuss so far in the data path what happens if we have exceptions. For example, you are adding two values. Last time I asked this question. If you're adding 32 bits to 32 bits, what is the expected output? 33 bits, right? It's always number of bits plus one. So in that case, if your output register is only 32 bits, that's really an exception because the output result in the register file will not be correct. You have what we call an overflow. Overflow is an example of a flag, an exception that you need to tell the user there is a problem, right? So you basically set that flag or set that exception. There are multiple types of exceptions. The exceptions that happens within the execution unit itself, sometimes we refer to as traps or flags. And the exceptions that happen, for example, because while you are in the normal path of the processor, you receive some input from an input-output device, right? Think about, for example, you are running something in your laptop, but then you use the mouse to click another application. In that case, you have to interrupt the original running process to respond to the mouse operation, right? So the I/O is interrupting the normal flow of the program to do something else. This also happens through exceptions and interrupts. Good. So a general differentiation in computer architecture is we say the things that happens within the execution unit itself, we call it exceptions. While the things that happen externally, we call it interrupts. Why again? Because the thing that would happen externally will interrupt the normal flow, while exceptions will not interrupt the normal flow, right? So here, that's why we say exceptions are synchronous. Why synchronous? Because they are within the CPU itself, so something external, and they are generated by the running application itself from the pipeline. I mean, divide by zero is an example. Exception, if you have an illegal instruction, that's another example. Interrupts are asynchronous. Asynchronous here means, they happen externally. They're not really aligned with the CPU clock. And then this generally happens because of an I/O request. Good. This topic is better discussed in detail in 4DS because embedded systems is all about really handling interrupts, exceptions, dealing with I/Os, right? And we will come back into this when we talk about pipelining, because if you have an exception that would stall the pipeline, you need to do something different. And if you are doing an out-of-order execution, it's even more problematic. So I would defer the detailed discussion of this into that time. But generally, why do we care about exceptions? Because simply, I need to embrace them into my implementation of the data and control path. Again, I told you, if I divide by 0, I need to write the circuitry in the ALU that says detect this is a division by 0 and then output a flag. So you need to take care of handling them. That's why you really implement the actual actions that are happening because of exception. Good. Okay, so now this is the last slide and we stop here. For the very first time we are in time. So performance of single cycle maps. So all what we discussed so far against a single cycle processor, right? As we said earlier, we're going to match everything to the original target performance, right? We want to measure performance of things and we see how we can improve performance. For the single cycle, it's very, very easy. It's a single cycle for every instruction. Every single instruction finishes with one cycle. So what will be my CPI? It's 1, right? And again, the CPI is the same for all instructions because I don't do anything different. So here the CPI is just 1, right? And if I want to calculate the total execution time, similar to what Maxim reports, for example, you have to have the total number of instructions and then multiply by 1, right? The problem with this is way too slow, right? If you finish only one instruction per cycle, you are hugely limited to the frequency of the processor, right? While in reality, as we discussed earlier, if I have already fetched it, I go back to my normal data path, and if I have already finished fetching one instruction and then I'm executing it, this whole circuitry here for the fetch is idle, so I'm not using it, right? And then, the same thing, the memory is also idle if I'm doing an add here. So you don't want to keep your hardware functioning, it's underutilized. If you want to improve performance, you want all the time, every single one of these is doing something. This something does not have to be of the same instruction. They could be of different instructions. And as we will see tomorrow, in reality, this something doesn't even have to be within the same program. It can be from different programs. So this is the concept of multi-threading, right? So we'll come into this discussion later on. But to improve performance, again, I can handle. I said we are done, but anyway. So simply, I can go through all these operations in parallel for pipelining, and this is what we're going to discuss tomorrow. Thank you.